Hello students, good afternoon to one and all. Myself Assistant Professor K.C.Hanchinal from Department of Electrical and Electronics, SECAB Institute of Engineering and Technology, Vijayapur. In the Model 3, in a design of a transformer, the one of the most important topic it is design of a tank with the cooling tubes it is. Okay, in today's session what we are going to discuss it is the derivation on or the designing part of the transformer tank with the cooling tubes it is. Okay, let me start with the derivation. See here the step-by-step derivation, I had written here. So see here, basically the transformers are provided with the cooling tubes it is. The first thing it is, the cooling tubes are provided in the transformer to increase what? Dissipating area, heat dissipating area itself. One more thing it is, the cooling tubes, why cooling tubes are necessary in the transformer, in the sense that if the temperature rise of the tank is beyond the permissible value, about 500 degrees Celsius, then cooling tubes are to be added, and it is very much needy to reduce the temperature rise it is. So that is the reason the cooling tubes are provided in the transformer tank to increase the heat dissipating area as well as to keep the temperature rise within the permissible limit it is. So then these cooling tubes, how they are mounted? So mounted on the transformer tank. So these tubes are going to be mounted on the vertical sides of a transformer tank it is. So getting my point? So next thing it is, these tubes, the tubes will also improve the circulation of a oil it is. Circulation of the oil it is going to be gets improved by the addition of or by the providing of the cooling tubes in the transformer tank it is. The oil which is flows in the transformer tank, the oil it is going to be flow in the transformer tank. How? By the principle of natural convection process it is. The convection process it is nothing but what? The transferring of heat from one place to the another by the movement of the fluids it is. That is going to be called it as what? Convection process. By this principle only, by this natural convection principle only, oil it is going to be flows in the transformer tank it is. So that is the reason, hence this type of a cooling it is going to be called it as a oil natural cooling. Getting my point? So next thing it is, whatever the heat it is going to be transferred from the core as well as the transformer windings to the oil it is, then what will happen? Oil it is going to be gets heated up completely. Then this heated oil or a hot oil it is going to be cooled by the natural air it is. So getting my point? So that is the reason. So next, one more thing it is, the tubes which by the circulation of the oil in the tubes, this will also improve the dissipation of loss by the convection process. So convection process means what I told here, the convection process it is nothing but the transferring of a heat from one place to the another by the movement of the fluids it is. Fluid it is nothing but what here? That is the oil here. So this is the reason the improvement in loss dissipation by convection process is equivalent to the loss dissipated by 35% of the total tube surface area. So basically one point I would like to clear to you. So the heat dissipation to the surrounding area, either it is through the proper mode or a media it is. Proper mode in the sense that either it is a convection mode or it is conduction mode or through the radiation process it is. So that is the reason, hence to account for this improvement in a dissipation loss by the convection process, what we are going to be doing here, to account for the just for the improvement in the dissipation of loss by the convection process, an additional 35% of a tube area, this is very important, additional 35% of the tube area it is going to be added to the actual tube surface area. What purpose we are going to be adding this 35% of tube area? So with the actual tube surface area. So why? In the sense that in order to improve the dissipation of loss by the convection process, keep it in a mind. So that is very important. So like next thing it is, okay, let me start with the derivation here. So see here, the first point what I had taken here, there are two important bits are there. Just what is the heading of this derivation? The design of a tank, transformer tank as well as the cooling tubes. There are two important terms are there. One it is the transformer tank and one more it is the cooling tubes. Getting my point? Keep it in a mind. Then what we have to do, let me start with the derivation. What area, surface area we have to take, surface area of the tank also we need to take, as well as the surface area of the tube also we need to take. So first thing it is the dissipating surface of a tank. Dissipating surface of the tank, that is equal to what? ST it is. Why I had represented like this, in the sense that surface means capital S I had taken here. Tank stands for small t here. Nothing but dissipating surface of a tank, it is ST. Next, what it is? This is about the tank, it is over. After this, in this tank only, the cooling tubes are going to be mounted vertically. So that dissipating surface also we need to take into consideration. So the dissipating surface of a tubes, that will be written as a, this is ST, nothing but a dissipating surface of the tank. Then what about tubes? It will be X times of this ST. Getting my point? So I hope these two are clear. So ST how I had taken here. Surface stands for S I had taken here. The tank means that is T I had taken here. So dissipating surface of the tubes will be equal to X times of this ST. So these are the consideration for dissipating surface of a tank as well as the dissipating surface of the tubes it is. Okay, next thing it is. Next, what I told here, what purpose we are providing these cooling tubes in a transformer tank? In order to improve in order to increase the heat dissipating area. Heat dissipation to the surrounding, it is nothing but loss, it is nothing but loss dissipated by the surface of the tank. By which process I told here? The dissipating of heat to the surrounding media with the help of the proper mode or a media I told here. So what are those modes? Either it is a convection mode, conduction mode or radiation mode here. But what I had considered here, the loss dissipated by surface of a tank, by which processes? One, it is radiation process, one more it is through the convection mode it is. So let me clear here. Here I had taken it as a 6 plus 6.5 it is. So first thing it is loss dissipated. The amount of heat dissipated to the surrounding with the help of a radiation process, it will be 6%. That is the reason 6 I had taken here. Then what about this convection process? That will be 6.5%. Getting my point? That is the reason. So 6 in the sense that the loss dissipated by the surface of the tank, it is through the radiation process, it is 6%, and through the convection process it is 6.5%. So next, which I had taken here, loss dissipated by surface of the tank, it is the dissipating surface of the tank, it is nothing but ST it is there. So that is the reason multiplied with the ST. 6 it is due to radiation process and 6.5 it is due to the convection process. Then dissipating surface of the tank, it is given by the ST. I had multiplied here ST. Then all together how much it will be? 12.5 times of ST. Keep it in a mind. Next, one more thing it is. So this is the loss dissipated by the surface of the tank by radiation and convection process. So next I would like to take only by the convection process. Getting my point? So this is all together radiation as well as the convection process it is. But I next need only in the sense that heat dissipating area, it is going to be improved with the help of the convection process. How it is going to be improved? By taking additional 35% of the tube area, it is going to be added to the actual tube surface area. Getting my point? So first let me consider here loss dissipated by the tubes by convection process. Convection process means how much it is there? 6.5% it is. 6.5 I had taken here. Next, in order to improve the total area, dissipating area through the convection process means additional 35% it is going to be added to the actual tube surface area. That is the reason I had taken here. So see here, that is the reason I had taken it is here a 35% more. Nothing but 135 it is, 100% is the actual tube surface area. In order to improve the heat dissipating surface by the convection process, additional 35% it is going to be added to the actual tube surface area. That is the reason 135 divided by 100 into what I had written? XST. XST I had taken here. This is the loss dissipated by the tubes. Loss dissipated by the tubes, it is nothing but dissipating surface of the tubes, it is XST it is there. So that is the reason what I had written here. Convection process 6.5. In order to improve it more, 35% of the additional tube surface area it is going to be added. That is the reason 135 divided by 100 I had taken. Here XST, it is nothing but the dissipating surface of the tube, because I am considering here tube only. So nothing but XST I had taken. So after solving this, you will get it as a 8.8 XST. Getting, I hope all of you clear with these things. Okay. So next we'll move on to see here. Then what it is there? So next thing it is, so these are the loss dissipated by radiation process as well as the convection process I have taken here, and alone convection process also I have taken here. Then what about total loss dissipated by this tank as well as the cooling tubes? How will write this one? By adding these two. See here, the total loss dissipated by tank walls and the tubes. How will write? This is first one, it is by the radiation and convection process, how much it is there? 12.5 ST, and loss dissipated by the tubes by convection process, it is 8.8 XST. It is 8.8 XST. So that is only by adding these two. By adding these two, we'll get the total loss dissipated by the tank as well as the tubes. It is getting. So add here. So 12.5 ST plus 8.8 XST. So after this, what is the common between these two factors? ST, I take it as outside, 12.5 plus 8.8x into the ST it is. Getting my point? So this is what heat loss dissipated, either it is a radiation process and convection process, and one more it is alone through the convection process I had taken here. Then what about actual total area of the tank walls and tubes? Actual area in the sense that, so these two actual areas means without any loss dissipation through the medias, nothing but radiation, convection, these processes are not going to be considering here. Then actual area, it is nothing but the sum of these two, dissipating surface area of the tank plus dissipating surface area of the tube it is. So that is the reason actual total area of the tank as well as the tubes, it will be equal to ST plus XST. So what is common here? ST, I will take it as a outside, 1 plus X will remains inside. So call this equation as a 2 here. So next thing it is, one more important it is, the actual total area also we got, and one more thing it is, total loss dissipated through the radiation or convection process also we got in the first equation as well as the second equation we got. Then finally, next what I would like to calculate, the how much amount of the loss it is going to be gets dissipated in per meter square of a area. For a particular area, how much amount of the loss it is going to be dissipated, I am considering here. So next thing it is, this will be the ratio of total loss dissipated. Total loss dissipated in the sense that either it is through the radiation and convection process to the total actual area, I will take it here. So from the equation 1 and 2, so total loss dissipated is how much? 12.5 plus 8.8 x into the bracket of the ST. To the actual area is how much? ST into the bracket of 1 plus x it is. Then ST will get cancelled. What is remaining here? So that will give the loss dissipated per meter square of a area. So that equation I will call it as a 3 it is. Getting my point? So this is the one reason. So in the basically I told that transformers are provided with the cooling tubes. First thing it is to increase the heat dissipation area, and second thing it is why we are providing the cooling tubes means whatever the temperature rise it is going to be exceeding the permissible, or if it is beyond the permissible value means in order to keep within the safer value, the cooling tubes are going to be providing. The first point it is with respect to the heat dissipation area, either it is through convection process or it is radiation I had calculated here. So next factor what I told here, to keep the temperature rise within the safer value, that is the reason the cooling tubes are going to be providing in the transformer tank. So next what we have to do, obviously we have to calculate the temperature rise in the transformer by providing with the cooling tubes. It is the temperature rise in a transformer that is represented by theta. So this will be equal to what? Total loss divided by loss dissipated. So we already calculated this loss dissipated. loss dissipated, how the loss of heat it is going to be dissipated, either it is a convection or it is through the radiation process. Is it right? So total loss means what? Total loss means there are power loss. Total loss, it is nothing but the power loss. We have a two different kinds of losses. One, it is the constant losses, one more it is copper losses. Is it right? So constant losses, it is nothing but the iron losses. Iron losses means which losses it includes? Hysteresis losses as well as the eddy current losses itself. So that is the reason the total loss, it is the sum of iron loss. Pi, it is nothing but iron loss. Pc in the sense that it is copper loss. Altogether it will give the total loss. Is it right? So where Pi is iron loss, Pc is the copper loss. So this is total loss. Then divided by what it is there? Loss dissipated. How the heat it is going to be dissipated? Whether the either convection or radiation process. Getting my point? So that is the reason from equation 1 and 4 we can calculate this temperature rise. It is from equation 1 what it is there? Total loss dissipated by tank walls as well as the tubes by convection process as well as the radiation process I had taken here. So from this equation I will write it here. See here, the total loss, it is nothing but Pi plus Pc. Theta is equal to Pi plus Pc divided by loss dissipated by tank walls and the tubes. It is equation 1. Just to observe it. So that only I am substituting here. Getting my point? So after substituting, what you will get here? So this theta will be equal to Pi plus Pc divided by 12.5 plus 8.8x into the bracket of the St. Or this equation shall I write like 12.5 8.8x equal to Pi plus Pc divided by this theta I will take here, and this St was remaining here, this theta St. So what is constant here? X, it is the constant, because everything we know in this things. Is it right? So from this equation I will get for the value of x, it is x is equal to what? Pi plus Pc divided by theta St minus 12.5, that bracket complete. What is remaining here? 8.8 it is. 1 divided by 8.8 it is. Just you solve this for x, you will get this equation. Getting my point? So next unknown factor x we had calculated here. Then see this here. See here what it is, that dissipating surface of the tubes, that is equal to what? X times of the St it is. But we got the equation now, x value, x equation we got now. So next what shall I do? Then substitute for this x in this. Then total area of this cooling tube, it is x St it is there. We already got the equation for x now. So now you substitute here. Then total area of the cooling tubes, that is 1.1 divided by 8.8, that will be equal to Pi plus Pc divided by theta St minus 12.5 into St. It is x St. The x value just I had substituted here and multiplied with the St here. So this will be equal to what? So multiply this St inside, Pi plus Pc divided by theta St into St minus 12.5 into St. So this St and this St will, it is going to be gets cancelled. Then what is remaining now here? That is 1 divided by 8.8. So into the bracket of Pi plus Pc divided by theta plus 12.5 of St it is. So this equation we are going to be call it as a 7. So this will give the total area of the cooling tubes. It is total area it is going to give, but in that particular area how many number of tubes are there? So that how we are going to be calculating, in the sense that, so let me take, so first thing it is for one tube I am going to considering here the total area of the cooling tubes we can calculate by this equation number 7, but in that area how many number of cooling tubes are there? So that calculation it is going to be done with the help of the following procedure here. So let me take first one, it is let length of a tube it is LT. L stands for a length and small t stands for the tube it is. Second one it is diameter of a T. So diameter of the tube, D in the sense that diameter, T stands for the tube here. So I had considered, so in order to calculate the number of tubes in a particular area, so that is the reason the surface area of each tube that will be given by pi dt LT. So let me consider this tube will be like what? Cylindrical structure. It will be like a cylinder. So what is the formula for all of you familiar with the surface area of a cylinder? That is the formula. It is nothing but pi into d into L. It is there. pi into diameter into length it is. So you just check it. So what is the formula for surface area of a cylinder? Why? The tube will be like a cylinder only. The surface area of each tube, I take it as a pi into dt into LT. Just you Google it. What is the formula for a surface area of a cylinder? You will come to know. The tube will be in the form of a cylinder only. That is the reason the surface area of each tube, the formula will be pi into d into L it is there. But the tube I am considering here, that is the suffixes I have taken it as a t here. Pi dt LT here. Then what about total number of tubes in a particular area? How many number of tubes are there? So that will be represented by NT it is. Number in the sense that N, and the tubes it is sense that small t I had taken here. Getting my point? So this will be equal to the ratio of total area of tubes to the area of each tube. Total area of the tube we already calculated. Is it right? In that, among this one, area of a particular only one tube if we had taken means how many number of tubes are there in that particular tank, we can come to know. Is it right? So NT will be the ratio of total area of the tubes divided by area of each tube it is. So what is the formula total area of the tubes? So see the equation number 7. This is the total area of the tube it is. So 1 divided by 8.8 divided by 1 divided by 8.8, just you write as it is. 1 divided by 8.8 pi plus pc divided by theta minus 12.5 st I had taken here. So divided by area of each tube. Divided by area of each tube, it is pi dt lt. So shall I write like this? 1 divided by 8.8, that is pi dt lt into the bracket of pi plus pc divided by theta minus 12.5 st it is. So this equation will give the total number of tubes it is. So this is the very important derivation it is. One more thing it is, very important note it is here. See here. The standard diameter of a cooling tube. So what I had taken here, diameter of a tube. While solving the problems, if they didn't mention the diameter of a tube, means the standard value how much we have to take, that is 50 mm. So next thing it is, this length of a tube, sometimes they will give. If they didn't give means, if they didn't mention in the numericals means, the length of a tube, it will be equal to the, depends on the height of a transformer tank it is. If height of the tank, definitely they will give in the problem. So that height will be equal to the length of a tube you need to consider. Getting my point? So next thing what I told here, so these transformer tubes are going to be mounted vertically in the transformer tank it is. How it is going to be vertically, how it is going to be spaced inside, how it is going to be placed inside the transformer tank, in the sense that the tubes are arranged with the center to center spacing of 75 mm. How they are going to be done? With the providing from one tube to the another tube, centers to center spacing will be 75 mm it is. Keep it in a mind. While solving the numericals, if they didn't give the diameter of the cooling tube, then how much we have to take? That is 50 mm. This is the standard. If the length of the tube, if they didn't mention means, so this will be completely depends upon the what? Height of the transformer tank it is. Then after this only, the number of cooling tubes, how much from this equation, we'll get the number of tubes. So these tubes we should arrange it in a transformer tank. How it is going to be arranged? With the center to center spacing of a 75 mm we need to consider, and we have to do the arrangement. Getting? I hope all of you are getting. So this derivation. So thank you.